Welcome to the screencast on networked embedded systems. This screencast talks about wireless sensor networks, which are being deployed for the automation of large-scale supermarkets. Now, using automation in supermarkets has become a trend. Every supermarket is in a constant search of latest technology in order to improve their customer experience and also for easy maintenance of their stores. Now, one of the examples that I would like to start with is Amazon Go, where Amazon Go is a supermarket based out of the United States of America, where customers can just walk into the store, purchase the products they want without having to stand in long billing counters. So, Amazon Go uses the just walkout technology where customers just have to check in when they enter a store and they can just pick the products from the shelves and they can just add it to their cart and walk away without having to make the payment. And another technology in use in the supermarket domain is the smart cart technology, which is developed by a Finnish company, where tablets are attached on top of the shopping carts, where customers can browse for information about the products that they are looking for, and they can also find directions to the products which are stacked in a particular section inside a supermarket. And if in case they would also want to check if a product is currently available in the supermarket or not, they can also do that. So in this line of the new technological advancements in the supermarket domain, we add a new we add a new item, which is the smart label. Now, just before I talk about the smart label, let me first talk about some of the pain points which are being faced by the supermarkets and its customers. Now, for supermarkets, it is becoming difficult for them to update information about each and every product for a large number of products which are available in their stores. And also, at times when products are being purchased or not purchased, restocking the shelves is something that supermarkets would have to handle, and it requires a constant check on the products which are sold or not sold. And also, removing expired products is also a tedious process where they need to keep constant tabs on the products which are sold and not sold. And product labels would also have to be updated on a daily or a weekly basis based on the offers which are being provided. And this is again a tedious task. Now, from a customer standpoint, it is difficult for a customer to get additional or more information about the products. So just before you buy a product from a supermarket, you would generally read more information about the product, and at times this information might not be in the desired language of yours, and you might have to use some translation tools to get the information you need or talk to a supermarket staff to get this information. And also, for the customers, after they're just going to add the products to their cart, they will have to stand in long billing queues, which is really time consuming in order to build the products, make the payment, and then check out. Now, Smart Label is going to answer all these, is going to be the solution for all these pain points. And now let's first look at what are all the requirements which are being demanded for the Smart Label application. Now, one of the major requirements was to have a network that supports up to 8,000 nodes. And this was one of the biggest challenges that we had faced in designing this application. And the area that is required to cover is around 1,000 square meters, which might be the size of a particular supermarket, and the peak density that is expected is around 25 nodes per square meter, and also the peak load that is expected is close to 125 customers at a particular time. And the communication range per node is set to 10 meters. Now, one advantage that we had was that these nodes do not have any power or energy constraints as they are always plugged to power sockets. And some of the major requirements were low latency, high security, and also high reliability. Now, our solution to all these problems and that caters to these requirements is the use of smart label with wireless sensor networks. Now, as you can see in the figure, so we have a wireless sensor network that comprises of different smart labels. Now, whenever a customer wants to find information about a particular product, all they have to do is take out their mobile phones, place their phones next to the smart label for a particular product, and this would give them the information about the product. So for this, we use NFC chips. We're using near field communication. Information is being transferred from the sensor labels over to the customer's mobile app. And once the customers read through the product description or the product information in their desired language, they can just add the product to their virtual cart. And after adding the product to the cart, what happens is this this gets updated in the database of the supermarket so that the supermarket can keep tabs on the number of products a particular customer has purchased or the quantity of the products that a customer has purchased. And this would help the supermarket as well when it comes to restocking the product shelves. For this application, we selected the physical and MAC layers of the IEEE 802 period 15 period 4 protocol. This was because of the low cost and the simple implementation which was offered by this protocol. And also, the amount of data that was needed to be transmitted was very small. And this was also one of the reasons why we went ahead with this protocol. And for the physical layer, a 2.4 gigahertz frequency band was selected. Also, DSSS, which is the direct sequence spread spectrum, along with OQPSK or SQPSK, which is the offset quadrature phase shift keying modulation, was selected. And for the MAC layer, we selected the non-beacon enable mode. And this was because the application doesn't have high data traffic, and also there isn't a need for the beacon packets to be sent periodically. Also, non-beacon enable mode was able to offer better results in terms of latency and than the beacon enable mode for similar applications like these. Several networking standards were considered for this application, and that include Thread, Zigbee Alliance Standard, and Bluetooth. Now, Thread is one of the newly released networking protocols which has future-proof features that piqued our interest. However, it had a drawback where it was able to support networks which can have a maximum of only 300 nodes. And also Bluetooth, which is one of the widely used networking standards, was also considered, and it also had a healthy data rate of around 2 megabits per second. But similar to Thread, it had a drawback where it was able to support only up to 7 nodes in a network. Now, on the other hand, Zigbee Alliance Standard had a greater market penetration compared to the other networking standards, and it also had better security features which use 128-bit keys for its security related mechanisms. One of the biggest advantages of Zigbee was that it supports up to 65,000 nodes in the network. So from a scalability standpoint, if in case, let's say the supermarket wants to expand the number of nodes in the network, this can be done using Zigbee. Thus, we selected the Zigbee Alliance standard for our application. Several topologies which were available in the Zigbee network layer include the star, mesh, and the tree topologies. Star, as we all know, is a topology where the nodes can communicate directly with the coordinator, whereas in the mesh topology, the nodes can communicate with their neighbors, and it also uses AODV routing protocol, where this routing protocol discovers and establishes routes to the destination on demand. And the third one is the tree topology, where a parent-child relationship is established between the different nodes. We selected the tree topology for the network layer, and this was because of the simplicity of this topology, and also it offered better performance in terms of the latency and the lesser number of packet drops. And also in this topology, there wasn't a need for the routes to be discovered as the parent-child relation between the different nodes was established before. And for the hardware setup of this application, we selected the Nordic Semiconductor NRF 52840 system on chip. And this was selected to be acting as the central coordinator, the routers, and the end devices. Now, this central coordinator will be connected with the microchip ENC 424J6000 Ethernet controls. Now, some of the reasons why we selected this chip was because of its high performance capabilities and also because of the numerous peripherals which are contained in it. And that includes the integrated NFC chip, the near field communication chip, and also the QSPI, which is the quad serial peripheral interface. And it also supports some security features which uses the AES 128-bit encryption suite. For our application, several simulators were considered, namely ARMNet++, NS2, and NS3. Considering the amount of nodes in the network and the density of this network, we chose the NS3 simulator. NS3 is a discrete event network simulator which is aligned to the simulation needs of modern research. And this simulator is really intuitive and easy to debug, and it caters to the requirement of our simulation workflow. In this simulator, we use C++ programming language to develop our code, and while doing so, we use different modules and the different classes contained in them. Some of the modules we used were the LR wireless personal area network module, and the classes contained in this module were LRWPAN physical layer class and the LRWPAN MAC layer class. And other important classes that we use include the LRWPAN CSMA-CA class and the LRWPAN net device class. In the NS3 simulator, there's a NetAnim animator module which was used as the graphical user interface to show the simulation results. Now let's talk about the architecture of the wireless sensor network in the supermarket. Now what you see is a product shelf which could have a maximum of up to 50 columns and a maximum of up to 20 rows. Products are going to be placed on either sides of the shelves, and each and every product in the shelf will have a dedicated smart label which will act as a node. And on top of these shelves, we are going to place the routers. Now, this is the bird's eye view of a supermarket that has 10 shelves. The small red dots, which are densely packed and placed close to each other in a straight line, are the smart labels. Products are placed on either sides of a shelf, and thus we see densely packed red dots in a straight line on both sides of the shelf. Between these red dots placed in straight lines, we have four red dots which denote the routers, which would be placed on top of the shelves. And we have a coordinator placed at the center of the supermarket. Now, these are the steps we had taken for developing our code and for the simulation process. In our code, we have created and designed the nodes and the different devices, and then we assigned a short MAC address to each and every node and LRWPAN net device, which was initialized. And the position of each and every device was also set, and two callback objects were created per node. And these two callback objects are created for data indication and data confirmation. And for the routing protocol, we used two hop or three hop communication was needed, and that was set up too. And an end device which selects the closest router to communicate was also set up set up using an algorithm that we define. Data generation. For the data generation, we had designed the code to have the data to be generated at a random time frame, and the source node from which the data was generated was also set to be random. A data packet was defined to have a size of 100 bytes. The simulation experiments were conducted with different loads. We initiated the simulation with 25 customers to begin with, and then it was gradually increased by a scale of 25 until the maximum expected load, which is 125 customers, was reached. So we increased the load to 50 customers, and then 75 customers, and then 100 customers, and then 125 customers, which is the peak load. We had designed the code in such a way that one packet will be communicated per customer every 10 seconds during this simulation time of 30 seconds. Now let's look at the simulation results. And as you can see, 75 packets of data was transported for 25 customers. Since for one customer, you're going to have one packet of data transmitted every 10 seconds during the simulation that happens for 30 seconds. And this is going to be 25 into 2, which is 75 packets. Now, on either side of the graph, you're going to find different metrics. So on the left-hand side of the graph, we find the delay, which represents the delay in the communication of data packets. And on the right-hand side, we find the metric PRR, which stands for packet reception ratio. After analyzing our simulation results, we were able to arrive at these conclusions. We could confirm that the design of this wireless sensor network is feasible for a smart supermarket application. Also, the latency was observed to be low. However, we felt that the packet drop rate, which was around 35%, can probably be solved with a better algorithm in place. Now let's go to the simulation part of the project. As discussed in the slides, so we use the NS3 simulator for completing our simulation here. Now what you see on the screen on the left hand side is the terminal emulator, where we're going to refer to the file which has the code, and we're just going to compile the file. And on the right hand side, what you see is the file
containing the actual code. Since the simulation is going to take some time, we're just going to run the simulation, and followed by that, I'm just going to give you a brief overview of the code. Now, what we have done in the code is we have first created the nodes and the devices, and we have initialized them. And followed by that, the MAC addresses were assigned to these nodes and devices. And then a channel was created and configured with a maximum range that was set to be 10 meters. And unslotted CSMA, which is the MAC layer, was configured, and an optimum backoff exponent was set up here. The channel and the CSMA was assigned to each and every device which was created, and the position of the nodes were also configured. And in the simulation, the devices which start the communication and the time frame when the communication starts was also set to be random. An algorithm was created to calculate the destination address based on the closest router to each and every node. And on receiving the packet, the router uses another algorithm to send the packet to the coordinator or the nearest router based on distance proximity. And on receiving the packet, the coordinator displays, we have the code to display the status of reception, and the delay value is calculated and displayed in the terminal. Now let's go into the simulation in the GUI. So I'm just going to start the simulation in the GUI. Now these structures that you see here on the screen represent the different shelves in the supermarket, and these red dots represent the individual nodes, and these red dots, which are placed very close to each other, represent the product labels. And we also find the routers placed in between two different stacks of the product labels. And as you can see, a communication has been initiated by one of the nodes, and it sends it to the nearest routers. Now we have the coordinator here, and as you can see, after a router receives the packet, it sends the data to the nearest, to the central coordinator. Now let's go to the terminal and let's look at the simulation results. Now since the simulation takes some time, it hasn't displayed the results yet. So let's look at the results of the previous simulation. Now here we can find the packet reception status. So it says that the packet has been received by the coordinator, and we represent the status here too. And the delay of the packet reception is also calculated, and it's been displayed.